You probably picture the universe as a giant, ever-expanding balloon. A smooth, endless sphere of space stretching outward in every direction, with no edge, no boundary, no end. This is the image most of us were taught. It is the image scientists themselves used for nearly a century. But there is a quiet branch of cosmology that suggests this picture may be wrong in a way that is difficult to fully absorb. Advanced topology, the mathematics of how spaces are connected, suggests space itself might not be infinite at all. It might be folded, wrapped, stitched back to itself. A hall of mirrors, a finite chamber shaped like a 12-sided geometric solid, large enough to look infinite from the inside, but closed in a way that means the universe you see may contain ghostly repetitions of itself. The proposal has a name: the Poincaré dodecahedral space, a model in which the cosmos is a finite, positively curved volume, whose opposite faces are identified, glued together after a precise 36-degree twist. If this is correct, the universe is not a balloon. It is something closer to a cosmic kaleidoscope. By the end of this video, you will understand what cosmic topology actually means. You will understand why the cosmic microwave background, the oldest light in existence, is the central piece of evidence. You will understand what matched circles in the sky are, and why physicists searched for them, and what they found. You will understand the Poincaré dodecahedral model, the rival shapes, and what each one would mean about the nature of reality. And you will understand why a question about the shape of space is, in the end, a question about whether the universe is the kind of thing that could exist without a cause. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. To understand why the universe might be shaped like a dodecahedron, we have to begin with a distinction that almost no one outside of theoretical physics learns properly. The distinction between geometry and topology. They sound similar, they feel similar, but they are not the same, and the gap between them is where the strangest possibilities live. Geometry asks how space is curved. Topology asks how space is connected. This distinction sounds abstract, but it lies at the foundation of every modern attempt to describe the structure of reality. Geometry developed first, in the work of the Greek mathematicians, refined through the centuries until Gauss, in the 1800s, gave it the modern treatment of curved surfaces. Riemann, who was Gauss's student, extended the framework to spaces of arbitrary dimension. By the time Einstein needed a mathematical language to describe gravity, Riemannian geometry was waiting. Space-time, in the general theory of relativity, is a four-dimensional manifold, whose curvature is determined by the energy and momentum it contains. The Einstein field equations are equations about geometry. They are local equations. They tell you how the curvature at any one point relates to the matter at that point. They do not tell you anything about the global structure. They do not tell you whether the cosmos is finite or infinite. They do not tell you whether space is shaped like a ball, or a donut, or an infinite plane. That information lives in the topology. Topology, as a mathematical discipline, began in the work of Henri Poincaré, the French mathematician for whom the dodecahedral space is named, near the end of the 19th century. Poincaré was concerned with the question of how to characterize a space by the loops you can draw inside it. He noticed that some loops in a torus, the surface of a donut, cannot be continuously deformed to a point. They go around the hole. Others, in a sphere, can always be shrunk away. This insight, that the connectedness of a space can be detected by the behavior of loops, became the foundation of algebraic topology. Poincaré stated a conjecture about three-dimensional spheres that would not be proven for over a century, until the Russian mathematician Grigory Perelman finally established it in 2003, the same year that Luminet and his team proposed the dodecahedral cosmos. The classification of three-dimensional manifolds, the spaces in which our universe might live, became a mature mathematical subject in the decades between. Cosmology was slow to make use of these tools. For most of the 20th century, cosmologists treated the global topology of the universe as a question beyond the reach of physics. The local geometry was what mattered. The Friedmann equation, the dynamical heart of cosmic expansion, was derived without any commitment to a particular global topology. The standard practice was to assume the simplest possible structure, a simply connected space, and move on. Whether the universe was actually that way was not a question the data could address. The first serious challenge to this neglect came in the 1990s, as the cosmic microwave background data began to reach a quality that could potentially distinguish global topologies. The work of Cornish, Spergel and Starkman in 1998, which I will describe in more detail shortly, made the question observationally tractable for the first time. From that moment, the question of cosmic topology moved from pure mathematical speculation to genuine physical inquiry. It is still moving. It is one of the open frontiers of modern cosmology. You can demonstrate the difference on a single sheet of paper. Take a flat rectangle. The geometry of that rectangle is simple. It is Euclidean. Parallel lines stay parallel. Triangles add to 180 degrees. Now imagine taking the left edge of that rectangle and bringing it around to meet the right edge, so that a small ball rolling off the right side reappears on the left. The geometry has not changed. The rectangle is still flat in every local sense. But the topology has changed completely. The space is now finite. It loops back to itself. A bug walking in a straight line on that surface would eventually return to its starting point, having never noticed any boundary, any edge, any curvature. This is the central insight of cosmic topology. A universe can be flat and finite at the same time. It can be infinite in appearance and bounded in reality. The shape of space, in the deepest sense, is not just about how it curves. It is about how it closes. For most of the 20th century, mainstream cosmology assumed this question was settled. The standard model of cosmology, the model physicists call lambda cold dark matter, treats the universe as infinite, flat, and simply connected. Space stretches forever in every direction. Light travels outward and never returns. The universe has no shape because it has no edge to define a shape. This model works extraordinarily well at most scales. It predicts the relative abundance of hydrogen and helium produced in the first minutes after the Big Bang. It predicts the temperature of the cosmic microwave background to a precision that astonished its proponents. It predicts the way galaxies cluster across hundreds of millions of light-years. The lambda cold dark matter model has survived test after test, and its parameters have been measured to extraordinary accuracy by satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite of the European Space Agency. But there is a question hidden inside that model that the data has never quite been able to answer. How big is the universe? Not the observable universe, the part we can see, which extends about 46 billion light-years in every direction. That number is well measured. The Planck mission, launched in 2009, established the age of the cosmos at approximately 13.8 billion years, with the observable region stretching to a radius of 46.6 billion light-years. The diameter of what we can actually see is therefore around 93 billion light-years. But beyond that horizon, beyond the curtain of the most distant light, the model assumes the universe simply continues, infinitely, without end. It is an assumption, not a measurement, not a derivation, an assumption. And there is no observation, no instrument, no possible direct test that could ever falsify it. Because the universe might be finite, and that finiteness might lie beyond the horizon of our observation, hidden behind the last layer of light. In that case, the universe we describe as infinite would be like a goldfish describing its bowl as boundless because it has never reached the glass. The question of cosmic topology, then, is whether the universe is in fact a finite volume that merely looks infinite because we cannot see its edges, or whether it is genuinely infinite, with no boundary anywhere. This is a question of physical cosmology in its most fundamental form. And it is a question that the cosmic microwave background may be able to answer. To understand why the cosmic microwave background carries so much weight in the topology question, we need to understand what it actually is. And the history of its discovery is worth the detour. In 1948, three physicists working on the implications of the expanding universe, George Gamow, Ralph Alpher, and Robert Herman, predicted that the early cosmos must have been filled with thermal radiation. As the universe expanded, that radiation would have cooled. By the present day, they estimated, the temperature should be approximately 5 Kelvin. The prediction was made on theoretical grounds, with no available data to confirm it. For nearly 2 decades, it was treated as an interesting but unverified speculation. In 1964, Arno Penzias and Robert Wilson, 2 engineers at Bell Laboratories in New Jersey, were trying to calibrate a sensitive microwave antenna designed for satellite communications. They could not eliminate a persistent background hiss from the receiver. The signal was the same in every direction. It did not change with the seasons or the time of day. It was, as far as they could determine, coming from the sky itself. They cleaned the antenna. They removed pigeon droppings from the equipment. The hiss remained. When they consulted with a group of physicists at Princeton who were preparing to search for exactly this signal, the realization came. Penzias and Wilson had stumbled upon the relic radiation of the Big Bang. They received the Nobel Prize in 1978 for the discovery. The Cosmic Background Explorer, COBE, launched in 1989, made the first precise measurements. Its instrument confirmed that the spectrum of the cosmic microwave background is a near-perfect blackbody, the most precise blackbody spectrum ever measured in nature. Its temperature, 2.725 Kelvin, has been measured to extraordinary precision. COBE also detected for the first time the tiny variations in temperature across the sky. These variations, on the order of 1 part in 100,000, were the seeds of all later structure. The discovery was reported in 1992 and led to the 2006 Nobel Prize for George Smoot and John Mather. Stephen Hawking, on hearing the result, called it the greatest discovery of the century, if not of all time. The Wilkinson Microwave Anisotropy Probe, launched in 2001 and named after the late David Wilkinson of Princeton, mapped the cosmic microwave background at much higher resolution than COBE. Its first-year data, released in 2003, allowed cosmologists to determine the basic parameters of the universe to better than 1% precision. The age, the composition, the geometry, all of it became measurable. The first-year WMAP data is also the dataset in which the suppressed quadrupole was first noticed clearly. The data on which Luminet and his team built the original Poincaré dodecahedral proposal. Planck, the European Space Agency mission, was the next great leap. Launched in 2009 and named after Max Planck, the founder of quantum mechanics, the satellite mapped the entire sky in 9 frequency bands, with sensitivity approximately 10 times that of WMAP. Its data was released in stages between 2013 and 2018. The final results, including the polarization analysis, set the most precise constraints we have on the geometry, the composition, and the topology of the universe. It is the Planck data on which the most recent topology constraints are based. It is the Planck data that has, so far, not detected the matched circles that the Poincaré dodecahedral model predicts. With that background in mind, let me describe what the cosmic microwave background actually is. The cosmic microwave background is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen, and photons could finally travel freely through space without being scattered. That light has been traveling ever since. It has been stretched by the expansion of the universe, redshifted from visible wavelengths into the microwave range, and it now fills every direction of the sky at a temperature just 2.7 Kelvin above absolute zero. It is, in a real sense, the photograph, the universe as a newborn. Picture this for a moment. Every direction you look in the night sky, behind the stars, behind the galaxies, behind the dust and the gas, there is a wall of light, a surface of last scattering, a spherical shell from which the photons of the cosmic microwave background departed 13.8 billion years ago. We see that shell as it was then. We see, literally, the early universe imprinted across the entire celestial sphere. And the variations in that light, the tiny hot and cold spots, are the seeds from which every galaxy, every star, every world was eventually formed. The temperature variations are small. They average around 100 microkelvin above or below the mean, a fluctuation of about 1 part in 100,000. But they encode an enormous amount of information about the universe at the moment that light was released. Inflation, the rapid expansion of the universe in its first instance, the density and composition of matter, the geometry of space itself, and the topology. If the universe is finite, if it is wrapped back on itself, then the light from the surface of last scattering cannot fluctuate at scales larger than the universe is wide. The largest possible ripples are limited by the size of the cosmic container. Like sound waves in a small room, the longest wavelengths simply cannot exist. They get truncated, suppressed, cut off. And this is exactly what observers have seen. Both the Wilkinson Microwave Anisotropy Probe, which began returning data in 2003, and the Planck satellite, whose results were finalized in 2018, found that the cosmic microwave background has unexpectedly weak power at the largest angular scales. The quadrupole, the component of the temperature pattern that varies across roughly 90 degrees of the sky, is much smaller than the standard model predicts. The expectation from infinite lambda cold dark matter is a quadrupole power of around 1200 square microkelvin. The observation is closer to 250, a deficit of roughly 80%. What does it mean that the largest pattern in the largest map we have ever drawn is missing most of the strength it ought to have? For some cosmologists, it means nothing. Cosmic variance, the statistical noise that comes from having only one universe to measure, allows for occasional anomalies. The probability of a quadrupole this week from pure chance has been calculated at somewhere between 4 and 7%. Improbable, but not impossible. And so the mainstream view treats the deficit as a fluke, bad luck, a statistical accident in the only experiment we have. But for another group of cosmologists, the deficit is a signature, a fingerprint of a finite universe, a glimpse of the wall that bounds our cosmic chamber. And the most precise version of that hypothesis has a name: the Poincaré dodecahedral space. The proposal was published in the journal Nature in October of 2003 by a team led by the French astrophysicist Jean-Pierre Luminet, along with his collaborators including Geoffrey Weeks and Roland Lehoucq. They argued that the suppressed quadrupole in the cosmic microwave background, which had just been measured by the Wilkinson Microwave Anisotropy Probe, could be explained by a universe with the topology of a dodecahedron, a 12-faced polyhedron, the shape Plato once associated with the cosmos itself. The mathematics is precise. The model takes a regular dodecahedron, the geometric solid with 12 pentagonal faces, 20 vertices and 30 edges, and embeds it in a three-sphere, the three-dimensional analogue of the surface of a four-dimensional ball. In this construction, the faces of the dodecahedron are identified pairwise. Each face is glued to the face on the opposite side, but not directly. The gluing involves a twist of 36 degrees, a precise rotation before the surfaces are joined. This identification produces a finite, closed, positively curved three-dimensional space, a space in which light leaving one face reappears on the opposite face, having traveled across what looks like a boundary, but is in fact a portal back to the other side of the same room. If you lived in such a universe, and you traveled in a straight line long enough, you would eventually return to your point of origin. Not because you turned around, not because you reached an edge, but because the universe loops back to itself by design. The dodecahedron is the fundamental domain, the smallest tile, that repeats to fill all of three-dimensional space when projected onto its universal covering space. That covering space, in the Poincaré dodecahedral construction, is the three-sphere. And the binary icosahedral group of order 120 determines how the dodecahedron tiles it. The volume of a three-sphere of curvature radius r is 2 pi squared r cubed. The volume of the Poincaré dodecahedral space is exactly 1/120th of that, equal to pi squared over 60 times r cubed. The factor of 120 appears because that is the order of the binary icosahedral symmetry group that identifies the faces. A precise number, a geometric necessity, a cell of finite volume nested inside a universe that, from the inside, would look infinite. The binary icosahedral group is one of the rare mathematical objects with a perfect symmetry that appears in multiple places where it had no obvious right to appear. It is the symmetry group of the regular icosahedron, the 20-faced Platonic solid, lifted to its double cover. It has exactly 120 elements. It appears in pure algebra, in the classification of finite simple groups. It appears in the structure of certain solutions to the quintic equation, which the Norwegian mathematician Niels Henrik Abel proved cannot be solved by radicals. It appears in the architecture of the so-called 24-cell and 600-cell, the regular four-dimensional analogues of the Platonic solids. And it appears, unexpectedly, as the natural way to tile a three-sphere with dodecahedra. There is a finite number of regular tilings of the three-sphere. The dodecahedral one is the most refined, the most intricate, the most mathematically elegant, the closest, in some sense, to a perfect cellular structure. If the universe is the Poincaré dodecahedron, then the cosmos has a symmetry group that mathematicians had already discovered by pure abstraction before anyone thought to look for it in the sky. The translation operations that identify opposite faces of the dodecahedron are mathematical objects called Clifford translations. They are isometries of the three-sphere, meaning they preserve distances. They are also without fixed points, meaning they map every point to a different point with no exceptions. This combination is rare. Most rotations have an axis they leave invariant. Most translations only work in flat space. Clifford translations are a kind of rotation that acts like a translation everywhere at once. The dodecahedral identification requires 12 such Clifford translations, one for each pair of opposite faces, each carrying the face into its opposite partner with the precise 36-degree twist. Picture, if you can, what this means for an observer inside such a universe. You look in one direction. Light reaches you from approximately 13.8 billion light-years away, from the surface of last scattering. You look in the opposite direction. The light reaching you from there started in a different physical region. The two regions are correlated by the Clifford translation that identifies the faces. If you mapped the temperature carefully, you would find that the temperature pattern around the matched circle in one direction matched the pattern around the matched circle in the other direction, twisted by 36 degrees, repeated with a phase shift across the sky. We will return to this number. We will return to the specific value of 36 degrees. We will return to the question of why, if the universe took a particular shape, it took that shape and not another. For now, hold these numbers in your mind. They will become important. Because the Poincaré dodecahedral hypothesis is not just an aesthetic preference. It is a falsifiable prediction. It says that a universe shaped this way will leave a specific fingerprint on the cosmic microwave background, and it predicts the exact form that fingerprint will take. The fingerprint is called matched circles. The prediction of matched circles was introduced in 1998 by three American cosmologists: Neil Cornish, then at Case Western Reserve University, David Spergel of Princeton, and Glenn Starkman, also at Case Western. Their insight was simple to state, but profound in its implications. If the universe is finite, and if the fundamental domain is small enough to fit within the surface of last scattering, then we are seeing the same parts of that surface from different directions. Picture the geometry carefully. The surface of last scattering is a sphere centered on Earth. Every point in every direction at a distance of 13.8 billion light-years lies on that sphere. It is the boundary of what we can possibly see. Now imagine the universe is finite. The fundamental domain, the basic cell that tiles the cosmos, is smaller than that sphere. If you traveled to the edge of the cell and continued straight, you would reappear on the opposite face. But light travels both directions, so the photons coming to us from one part of the surface of last scattering could also reach us by a different path, by wrapping around the cell, from a different angular direction in the sky. The same physical region of the early universe would appear in two different places on our map. The technical name for this signature is matched circles. Where the surface of last scattering intersects the boundary of the fundamental domain, a circle is formed. And because the domain is identified with its opposite face, that circle appears twice on the sky, in two opposite directions, with the same temperature pattern repeated along its circumference. To make the geometry of the matched circles vivid, picture the situation in lower dimensions. Imagine you are standing inside a perfectly square room, whose four walls are mirrors arranged not as reflective surfaces, but as portals. The right wall connects to the left wall. The front wall connects to the back wall. You take a step toward the right wall, and you reappear on the left side of the room. Now imagine that you cannot physically reach any of the walls, but you can see the light bouncing through them. Light traveling from a candle in the corner reaches your eyes not only by the direct path, but also by paths that wrap around the room any number of times. The same candle appears in the sky as multiple copies, at multiple distances from multiple directions. The wall is not a barrier, it is a seam, a connection, a gateway from this side of the room to the other side, which is also this side. Now extend the picture to 3 dimensions and bend the walls into the curved faces of a dodecahedron, and you have the Poincaré model. Each of the 12 pentagonal faces is a portal that connects to the opposite face. The portals are not flat, they are curved, and each portal carries a twist of 36 degrees, so the light passing through one face emerges on the other face, rotated by that precise angle. The mathematical signature of this geometry, projected onto the cosmic microwave background, is the set of matched circles. The circles arise because the surface of last scattering is a fixed sphere centered on our position. The fundamental domain, the dodecahedron, is fixed. The intersection of the dodecahedral boundary with the spherical surface is a set of curves. Each curve is a circle, in the geometric sense, on the sphere. Each circle appears twice, because the boundary is identified with its opposite face. The 2 appearances are related by the Clifford translation that performs the identification. The matched circle test was designed by Cornish, Spergel and Starkman to detect exactly this configuration. If the temperature profile around one circle matches the temperature profile around its partner, twisted by the predicted phase, you have evidence of cosmic topology. For the Poincaré dodecahedral model, the prediction is precise. 6 pairs of matched circles. 1 pair for each of the 6 pairs of opposite faces. Each pair separated by approximately 120 degrees on the sky. Each circle the same radius. Each pair related by a 36-degree phase rotation, the twist that defines the identification of opposite dodecahedral faces. And the radius of the matched circles for the best fit model would be approximately 11 degrees. This is a testable claim, a specific signature, a pattern that should appear in the cosmic microwave background if the universe is dodecahedral and should not appear if it is infinite. The mathematics of the prediction was developed thoroughly by Cornish, Spergel and Starkman through the late 1990s and into the 2000s. And when the high-resolution data from the Wilkinson microwave anisotropy probe arrived, the search began. The first major analysis of the matched circles hypothesis using actual data was performed by Polish astronomer Bałdywan Raukamar, working at Nicolaus Copernicus University in Torun. In 2004, Raukamar and his collaborators reported a tentative detection, a correlation in the WMAP first-year data in the configuration predicted by the Poincaré dodecahedral model, with a phase consistent with the 36-degree twist. The statistical significance was modest. The chance probability was estimated at around 7%, not a robust detection, but a hint, a possible glimpse of the cosmic kaleidoscope. For several years, the hint sustained interest in the topology hypothesis. Luminet published a book in 2008 called The Wraparound Universe, presenting the case for finite cosmology to the public. Other groups attempted independent analyses. New methods of detecting matched circles were developed. The community waited to see whether better data would confirm or refute the signal. The follow-up analyses were less encouraging. In 2008, Bartosz Lu and Bałdywan Raukamar, working with the third-year WMAP data, reported that the matched circle signal was consistent with an infinite, simply connected universe at the 68% confidence level. In statistical terms, this is roughly 1 sigma, almost no evidence. A null result that did not rule out the dodecahedron, but did not support it either. The earlier hint had faded into the noise. When the Planck satellite, launched by the European Space Agency in 2009, returned its full dataset, the topology community waited. Planck had 3 times the angular resolution of WMAP and approximately 10 times the sensitivity. If the matched circles were real, Planck should see them clearly. The Planck collaboration performed extensive searches. No statistically significant matched circles were found. The 2013 Planck results and the more refined 2018 polarization results were consistent with a simply connected universe at all scales tested. The matched circles, if they exist, are below the detection threshold of even our best instruments. The Poincaré dodecahedral model has not been falsified. It has been pushed into statistical tension. The window in which it can survive has narrowed, but it has not closed. Why has it not closed? Because the only way to rule out a finite topology completely is to detect light from beyond the fundamental domain. If the universe is smaller than the surface of last scattering, the matched circles must be detectable. If the universe is just barely larger, or larger by a significant margin, the wrapping happens at scales we cannot see. The matched circles would not exist in our visible region. The topology would be real, but undetectable, and our observation of an infinite-looking universe would be misleading. In other words, what the Planck data tells us is that the universe is at least as large as the observable region, with high probability. Whether it is much larger, infinite, or only slightly larger remains genuinely open. This is one place where the foreshadowed assumption I asked you to hold begins to strain. We have a model, lambda cold dark matter, that assumes the universe is infinite. We have data that is consistent with that assumption but does not require it. We have an anomaly, the suppressed quadrupole in the cosmic microwave background, that the infinite model treats as a statistical fluke, and a finite model treats as a fingerprint. And we have no observation that could ever decisively distinguish between the two possibilities from inside our cosmic horizon. The question of the size of the universe is, in this fundamental sense, beyond the reach of empirical science. We can constrain the answer. We cannot determine it. The Poincaré dodecahedral model is one possibility among several. It is not the only candidate for a finite cosmic topology. The mathematical landscape of finite three-dimensional manifolds is enormous. Each one corresponds to a possible shape of space. The flat 3 torus is another candidate. Imagine the rectangular surface I described at the beginning of this exploration, but extended to 3 dimensions. Take a cube. Glue each pair of opposite faces together without any twist. Light leaving the right face reappears on the left. Light leaving the top reappears on the bottom. The geometry remains flat. The topology is finite. The volume is determined by the size of the cube. This model also predicts matched circles, but in a different pattern. 4 pairs of circles, generally in the simplest version. More complex variants with rotations are possible. A recent collaboration of cosmologists, the so-called compact group, has analysed twisted torus models in detail. They find that simpler versions can be ruled out within the observable horizon, but more complex configurations remain consistent with the data. The three-sphere is another candidate. The original closed universe model proposed by Einstein in 1917, before the discovery of cosmic expansion, before the development of any data. A finite, positively curved cosmos with no identifications, no twists, no wrapping. The simplest topology consistent with closure. But the three-sphere is now severely constrained by Planck. The observed value of the total density parameter, omega total, is 1.0003 plus or minus 0.0014, almost exactly 1. Almost exactly the boundary between an open universe and a closed one. A pure three-sphere would require omega total greater than 1. The data is consistent with that to within errors, but the deviation from flatness is too small to be significant. The hyperbolic manifolds are another family of candidates. These are finite, negatively curved spaces, like the Weeks manifold, the smallest known closed hyperbolic three-manifold. Such universes have intricate tiling patterns, often involving identifications across many faces. The Planck data largely disfavors these models if their fundamental domains are smaller than the horizon. Some marginal hints in the WMAP data prompted speculation, but the more sensitive Planck observations have not confirmed them. And then there is the standard model, the infinite flat universe. No identifications, no edges, no wrapping. A cosmos that extends, by assumption, in every direction without end. This is the working hypothesis of the lambda cold dark matter framework. It is the model that fits the bulk of the data with the fewest assumptions. It is the position of cautious orthodoxy. And it is, as we have seen, an assumption rather than a result. What does it mean that the cosmos, the entirety of physical reality, may have a shape we have spent a century failing to detect? What does it mean that the largest possible feature of the universe, its global geometry and topology, is on the very edge of what our instruments can see? The Planck satellite is the most sensitive instrument ever built for the study of the cosmic microwave background. It can distinguish temperature variations of less than 1 microkelvin. It mapped the entire sky in 9 frequency bands. It cost approximately 700 million euros and required 20 years of development. And it cannot definitively tell us whether space is finite or infinite. We have built the most powerful sensor ever made and pointed it at the universe. And it has come back with an answer of perhaps. There is one more piece of this puzzle that the standard model has trouble explaining. It is the precision of the curvature itself. The Friedmann equation governing cosmic expansion tells us that the curvature of space depends on the relationship between the actual density of the universe and a quantity called the critical density. The critical density, given the current expansion rate, is approximately 5.3 times 10 to the minus 27 kilograms per cubic meter. If the actual density exceeds this value, the universe is closed and positively curved. If it falls short, the universe is open and negatively curved. If it matches exactly, the universe is flat. The measurement gives a ratio almost exactly equal to 1. The total density of matter and dark energy is balanced to better than 2 parts in 1,000 against the critical value. This balance must have held at every moment in the universe's history. And at the earliest moments, the balance must have been even more extreme. Trace the calculation backwards. The deviation from perfect flatness grows over cosmic time. If the universe is approximately flat today, it must have been astonishingly flat in the past. At the Planck time, the earliest moment that current physics can describe, approximately 10 to the minus 43 seconds after the beginning, the density of the universe had to match the critical value to a precision of 1 part in 10 to the 15th. A 15 decimal place agreement between 2 enormous numbers. Any deviation from that precision, in either direction, would have produced a universe radically different from the one we see. Slightly too dense, and the cosmos would have collapsed before galaxies formed. Slightly too sparse, and matter would have dispersed before any structure could condense. This is the flatness problem. It is one of the oldest motivations in modern cosmology for theories that explain why the initial conditions of the universe took the values they did. The standard answer is the theory of cosmic inflation, developed in the early 1980s by Alan Guth, Andre Linde, and others. Inflation proposes that the universe underwent a brief period of exponential expansion in its first instance, during which any initial curvature was stretched out to undetectable smallness. A region of space that started slightly curved would, after inflation, appear flat to any observer within it. The fine-tuning of the present is explained by the dynamics of the past. Inflation is an elegant idea. It explains the observed flatness, the observed homogeneity, the observed isotropy of the cosmic microwave background. It predicts a nearly scale-invariant spectrum of primordial fluctuations, which matches the data. It is the dominant cosmological framework of our age. But it is not without its own difficulties. Inflation requires a specific kind of field called the inflaton, with specific potential energy properties whose value at the beginning of inflation must itself be fine-tuned. The problem of the universe's improbable flatness is solved by introducing a new theory that itself depends on improbable conditions. We will return to this. The pattern of explanation, followed by deeper explanation, followed by deeper fine-tuning, is one we will see again. For now, hold the picture in your mind. A universe whose total density is balanced to extraordinary precision against the critical value. A cosmos whose geometry hovers exactly on the boundary between closed and open. A flatness that the standard model treats as a coincidence to be explained, but cannot fully explain without a deeper coincidence. And a topology, the question of whether space is wrapped or open, that current observations cannot resolve. The Jean-Pierre-Luminet hypothesis specifically predicts a slightly closed universe, with omega total approximately equal to 1.018. The Planck measurement gives 1.0003 plus or minus 0.0014. The dodecahedral value lies about 13 sigma above the measurement. From the standpoint of pure data, the model is intention. But omega is the average over the entire universe. If the universe is finite and only slightly closed, with a fundamental domain comparable in size to the observable horizon, then our measurements average over both the small curvature inside the cell and the apparent flatness imposed by the topology itself. The measurement and the model do not directly contradict. They constrain each other in ways that depend on the still unknown global structure of space. And so, the question of cosmic topology, the question of whether the universe is shaped like a dodecahedron, or a torus, or a sphere, or an infinite plane, remains open. Not because the data is inadequate, but because the question reaches the limits of what data can answer. We cannot see beyond our cosmic horizon. We cannot run another universe to gather statistics. The cosmic variance of large-scale modes places a hard floor on the precision of any test. The shape of the universe may be hidden behind the curtain of the past light, forever beyond our investigation. What does it mean that the universe could have a shape we are physically unable to detect? What does it mean that the fundamental geometry of reality is, by the structure of reality itself, partly unknowable? This is where we must turn our attention. Because if the question of cosmic topology cannot be fully resolved by observation, then any answer we give to it depends on the framework we bring to the question. And that framework is the deeper subject of this exploration. The assumption that the universe is the kind of thing that just is, without explanation, has consequences. Some of those consequences become visible only when we ask, what do these specific numbers mean? Why is the dodecahedron candidate's twist exactly 36 degrees and not some other value? Why is omega so close to 1? Why is the quadrupole so precisely the value it is, neither so low as to falsify the standard model, nor so high as to confirm it? We are building toward something. Stay with me. Let me return to the foreshadowed assumptions. I asked you earlier to hold the precise numbers in your mind. The 36-degree twist of the dodecahedral identification. The factor of 120 in the volume ratio between the dodecahedron and the covering sphere. The value of omega total at 1.0003. The 15 decimal place agreement between the early universe density and the critical value. I ask you to hold these numbers because the standard cosmological story, the lambda cold dark matter model with inflation, treats most of them as either lucky coincidences or as the dynamical outputs of fine-tuned initial conditions. The materialist position, the view that the universe is the product of nothing more than unconscious matter operating under physical laws, requires that these numbers be either accidental or the natural output of deeper laws that themselves are accidental. It is worth examining whether this position survives scrutiny when we look closely at what it actually claims. There are several specific claims that have accompanied the modern discussion of cosmic origins. Each of them has been made by serious scientists. Each of them has been popularized in books and lectures and interviews. Each of them is presented as the rational alternative to the conclusion that the universe was caused by an intelligent source. Let us take them up one at a time, and let us test them. The first claim is that the universe came from nothing. The argument was made most prominently in 2012 by the American cosmologist Lawrence Krauss in his book, A Universe from Nothing. Krauss argued that the laws of quantum mechanics, combined with the dynamics of gravity, permit a universe to spontaneously emerge from a state of zero net energy. The positive energy of matter, on his account, is balanced by the negative energy of the gravitational field, leaving a total of zero. From this perspective, he argued, the universe is the kind of thing that can arise without a cause. Stephen Hawking made a related argument in his 2010 book, The Grand Design, written with Leonard Mlodinow. He proposed that the laws of physics, particularly the law of gravity, allow universes to nucleate from nothing as a quantum event. The argument, in his framing, was that the existence of the universe does not require a creator. The argument fails, and it fails for reasons that the proponents themselves implicitly acknowledge. The failure is hidden in the definition of nothing. When Krauss says nothing, he does not mean nothing. He means a quantum vacuum, a state with no particles but with quantum fields, a state with no matter but with laws of physics, a state with no objects but with mathematical structure. This is not nothing. This is something. It is something whose existence is itself unexplained. Consider what genuine nothing would be. No matter, no energy, no fields, no laws, no space, no time, no probability, no potential, no mathematical structure, no possibility of anything. From that state, nothing could come, because the state itself permits nothing. Krauss's argument is that something can come from this not quite nothing. But this is not the answer to the question that has been asked. The question is why there is something rather than nothing at all. The answer that you can get something from almost something is not an answer. It is a redefinition of the question. Hawking's argument has the same structure. Gravity, he says, can produce universes. But gravity is something. The law of gravity is something. The mathematics that describes gravity is something. Where did the law of gravity come from? Hawking has no answer. The argument bottoms out in an unexplained brute fact about the existence of certain laws, certain structures, certain capacities of nothing that is actually something. This is the cosmological argument in its classical form. Whatever begins to exist has a cause of its existence. The universe began to exist. Therefore, the universe has a cause. The argument was articulated by medieval philosophers who built on insights from antiquity. But its logical force does not depend on its history. It depends on the inescapable observation that nothing cannot produce something, and the universe is something. The proponents of the universe from nothing argument know this. That is why they redefine nothing. The redefinition does not solve the problem. It moves the problem. What does it mean that the most prominent argument for an uncaused universe relies on a definition of nothing that, on inspection, turns out to be a definition of something? It means the argument is not what it claims to be. It is not a demonstration that the universe needs no cause. It is a demonstration that the proponents do not wish to confront the cause that the evidence implies. The second claim is that fine-tuning is an illusion. The precise values of the cosmological constants, the proponents say, only appear fine-tuned because we are observing the universe from inside the one configuration where observers can exist. The fine-tuning, on this view, is a selection effect. We see what we see because we could only see what we could see. This is the anthropic principle. In its weak form, it is undeniable. We are obviously observing a universe compatible with our existence. We could not be observing one incompatible with it. But in its strong form, the anthropic principle is used to explain away the precision of the constants by appealing to a multiverse of countless universes with random parameters, of which ours happens to be one of the rare habitable cases. The multiverse is the standard naturalistic response to fine-tuning. It is invoked in cosmology, in particle physics, in the foundations of quantum mechanics. It is the explanatory move of last resort whenever the precision of the universe becomes uncomfortable. The argument fails for several reasons. Consider what it actually claims. It claims that an unobserved, undetectable, mathematically required infinity of additional universes exists. It claims that each of these universes has different physical constants. It claims that the mechanism by which they generate themselves is itself outside the scope of empirical science. And it claims that this entire structure is a more reasonable explanation for the observed values of our constants than the proposal that the values were chosen. This is an extraordinary claim. The multiverse is not a measurement. It is not a prediction. It is not a derivation. It is a hypothesis introduced specifically to avoid the conclusion that the universe shows signs of design. The argument runs roughly as follows. The constants are too precise to be accidental. Therefore, they must be either chosen or selected. We do not want them to be chosen. Therefore, they must be selected. Selection requires a population. The population is the multiverse. The cosmologist George Ellis, a long-time collaborator of Stephen Hawking, has written extensively on the multiverse. In a 2007 essay in Scientific American, Ellis argued that the multiverse, in its standard formulations, lies outside the boundary of testable science. He noted that no observational test of the multiverse exists in principle. Other universes, by definition, do not interact with ours. Their existence cannot be confirmed or denied. Even Martin Rees, the British Astronomer Royal and an advocate of the multiverse, has acknowledged that it is, at best, a metaphysical hypothesis dressed in the vocabulary of physics. He has compared the question to the kind of speculation that exceeds the proper limits of empirical science. And the multiverse does not, in any case, solve the problem it is invoked to solve. Suppose there is a mechanism that generates infinitely many universes with varying constants. That mechanism is itself a specific kind of thing. It has specific properties. It produces specific distributions. The probability that a mechanism would exist with the right properties to generate at least one habitable universe is not zero, but neither is it one. The mechanism is itself fine-tuned. The problem is not solved. It has been moved upward in the chain of explanation. Behind every set of fine-tuned constants, there is a fine-tuned multiverse generator. Behind that, there must be a fine-tuned meta-mechanism. The regress does not terminate at a multiverse. It terminates only at something uncaused, eternal, and self-sufficient. And what is uncaused, eternal, and self-sufficient is precisely what the theistic tradition has called the Creator. What does it mean that the most ambitious naturalistic explanation for fine-tuning is itself a hypothesis whose explanatory power depends on fine-tuning? It means the explanation is not an explanation. It is an evasion. The third claim concerns the role of science itself. The argument is that we should trust methods of empirical investigation to eventually resolve all the questions that currently puzzle us. The gaps in our understanding on this view are temporary. Today, they may be unexplained. Tomorrow, they will yield to the advance of science. There is no need to invoke a creator to account for what we do not yet understand. The accusation often made is that any appeal to design represents a God of the gaps fallacy. As science progresses, the gaps shrink. The creator hypothesis loses ground. The argument has rhetorical force, but logical weakness. It is itself a faith claim. The claim that future science will eventually explain everything is not a scientific claim. It is a prediction about the future progress of an enterprise whose limits are not known. It is the very kind of unfalsifiable speculation that the proponents accuse the design hypothesis of being. And the gaps in current explanation are not random. They cluster around a specific kind of question. They cluster around the questions of why anything exists, why the laws of physics take the form they take, why the constants of nature have the values they have, why the universe is intelligible to mind. These are not technical gaps in the way that the structure of DNA was a technical gap before the work of Watson and Crick. These are foundational questions about the nature of reality itself. They are the kind of question that empirical science, by its method, may not be equipped to answer. The physicist Eugene Wigner, in a famous 1960 essay, called the effectiveness of mathematics in describing the physical world unreasonable. He meant something specific. He meant that mathematics, the product of human reflection, turns out to apply to the universe with a precision and a scope that no naturalistic theory of mathematical reasoning has been able to explain. Why is the universe legible to mathematics at all? The standard models of physics use differential geometry, group theory, abstract analysis. These tools were not developed to describe the universe. They were developed by mathematicians pursuing pure abstraction. And yet they fit. The cosmic topology of the Poincaré dodecahedral model uses the binary icosahedral group, a structure originally studied for its own algebraic interest. The structure appears in cosmology not because cosmologists put it there, but because it appears naturally in the geometry of three manifolds. Why does the universe respect a mathematical structure that was discovered before it was needed? Wigner himself called the situation a miracle. He used the word deliberately. He did not mean that he was endorsing a religious view. He meant that the situation has no naturalistic explanation. The intelligibility of the universe is a brute fact on the materialist account, a fact for which no further explanation is given or asked. But intelligibility is not a brute fact. It is the kind of feature that, in every other context where we observe it, implies a mind. A book written in a language we recognize implies an author who knew that language. A computer program that runs implies a programmer who designed it. A physical system that obeys a mathematical structure implies, at minimum, that the mathematical structure is somehow embodied in the physical system. The deepest naturalistic account of this fact is silence. The fact is registered, it is not explained. What does it mean that the most fundamental property of reality, its capacity to be understood, is unexplained by the very view that claims to explain everything? It means the view is not what it claims to be. Consider the precision of the constants that appear in our discussion. The total density parameter, omega total, must be within a few parts in 1,000 of 1 for the universe to evolve a structure capable of supporting observers. The cosmological constant, lambda, the energy density of the vacuum, has an observed value approximately 122 orders of magnitude smaller than the value naive quantum field theory predicts. This is, in physicist Steven Weinberg's words, the worst prediction in the history of physics. The mass scales of particle physics, the strength of the strong nuclear force, the mass of the electron. Each of these has a permitted range, and the actual value lies within an extraordinarily narrow window inside that range. Roger Penrose, in his 2004 book The Road to Reality, estimated that the precision of the initial conditions of the universe, the so-called past hypothesis required for the second law of thermodynamics to operate as it does, corresponds to a probability of approximately 1 in 10 to the 10 to the 123. The exponent itself has 123 digits. It is a number larger than the human mind can hold. It is the probability that, given a randomly chosen universe state, you would happen to find yourself in one capable of supporting the cosmological structure we observe. It is worth pausing to consider just how unimaginable a number that is. Consider that the number of atoms in the entire observable universe is roughly 10 to the 80, a number with 80 zeros after it, a number so large that no human being can directly grasp it. Penrose's estimate of the initial fine-tuning of the universe is one part in a number whose exponent is itself 123 digits long. The number of zeros after the 1 in the denominator exceeds the number of atoms in the universe by a factor that itself cannot be written in any reasonable notation. To call this a coincidence is not to provide an explanation, it is to abandon the project of explanation. Consider an analogy that may help. Picture an archer firing a single arrow across the entire observable universe, a distance of approximately 93 billion light-years. The target is a single atom located on the opposite side of that distance. The atom is 1 in 10 to the 80th in number. Penrose's estimate of the precision of the universe's initial state is more improbable than this archery feat by a factor that itself exceeds the number of atoms in the universe by an exponential amount beyond comprehension. The archery shot, in the analogy, is straightforwardly impossible. The cosmological precision of the universe we observe is, on materialist accounts, simply true, by chance. This is not how rational inference works. When we observe a configuration whose probability under one hypothesis is essentially zero, and whose probability under another hypothesis is reasonable, the rational inference is to the second hypothesis. The materialist account treats the universe as a configuration whose probability is essentially zero and asks us to accept it as a brute fact. The theistic account treats the universe as a configuration whose probability under the design hypothesis is reasonable and asks us to accept that something with the relevant power, knowledge, and will produced it. Penrose was not making an apologetic argument when he wrote his estimate. He was offering, with characteristic honesty, the consequence of what the equations and the observations together imply. The implication is staggering. The implication is that the universe is not a random throw of cosmic dice. It is an extraordinarily precise arrangement. The implication that any reasonable mind should draw is not silence, not chance, not future science of the gaps. The implication is the conclusion that the cosmological argument has always drawn. Whatever set those initial conditions had the capacity to do so, the knowledge of what was required, and the will to enact one specific outcome from an unimaginably vast space of alternatives. Power, knowledge, will. These are the marks of mind. They are not properties that arise from unconscious matter, no matter how cleverly we name the unconscious processes we appeal to. The materialist tradition has spent centuries trying to construct accounts in which mindless processes produce mind-like outputs. The accounts grow more elaborate. The fine-tuning grows more severe. The brute facts that have to be accepted without explanation grow more numerous. At every step, the simpler conclusion sits waiting, untouched. The simpler conclusion is that the universe was made by something whose nature is exactly what the data implies. Something with the capacity to do, the knowledge of what is, and the freedom to choose what shall be. Penrose was not making an apologetic argument. He was estimating, using his own assumptions, the degree of fine-tuning required by current physics. His estimate is shocking. It is so far beyond chance that the word chance loses meaning. To attribute the observed precision to chance is not an explanation. It is a refusal to explain. There is a useful analogy here. Picture a combination lock with 26 dials. Each dial runs from 0 to 1,000,000,000,000. The lock opens only when all 26 dials are set to specific values, not approximately, exactly. The probability of hitting the right combination by random rotation of the dials is a number so small it has no useful analogy. Now consider what makes the cosmic situation stranger than this lock. The dials were not set by anyone turning them. They appear to have come preset from the beginning. Preset to the configuration that permits stars, planets, chemistry, biology, observers. Preset to the configuration that permits a being to ask why the dials are set this way. If you came upon such a lock, in such a configuration, and someone told you that the dials happened to fall into the correct position by accident, you would not believe them. You would assume there was a locksmith. You would infer the locksmith from the lock, even if you never saw the locksmith. The product would imply the maker. The universe is the lock. The constants are the dials. The fine-tuning is the configuration. The materialist position requires us to believe that the dials fell into place without anyone setting them. And not just any configuration, the configuration that produces observers. The configuration that produces beings capable of recognizing the configuration. The configuration in which a creature evolves to look back at the dials and ask why they are set as they are. What does it mean that the universe is configured in a way that permits the question of its configuration to be asked? It means the universe is not what materialism describes. It is what the cosmological argument has long described: the product of a maker. Let me draw one more thread together before we conclude. The question of cosmic topology, the question of whether the universe is shaped like a dodecahedron or a torus or an infinite plane, intersects with the question of fine-tuning in a way that deserves attention. If the universe is finite, with a specific topology, then that topology is itself a feature of reality that requires explanation. The Poincaré dodecahedral model, for instance, requires a precise value of omega total close to 1.018. It requires a specific twist of 36 degrees in the identification of opposite faces. It requires a specific symmetry group, the binary icosahedral group with 120 elements. None of these are derived from deeper principles. None of them are explained by the model itself. They are the geometric parameters that define the shape. And the shape is the shape it is. If the universe is the 3 torus, the fundamental cell has specific dimensions. If it is a hyperbolic manifold, the topology is one specific member of an infinite mathematical family. If it is the infinite flat universe, then the assumption of infinity is itself a choice not derived from observation, a choice not derived from theory, a choice that simply asserts a particular global structure. In every case, the global geometry of the cosmos is a parameter that does not derive from physics. It is a specification, a boundary condition, a configuration that had to be set. The materialist position requires that the configuration be a brute fact. The theistic position recognizes the configuration as the kind of thing that, in every context where we observe specification, points to a specifier. The Poincaré dodecahedron, in particular, has an aesthetic resonance that is hard to overlook. The dodecahedron was one of the 5 Platonic solids, the geometric shapes that the ancient philosopher Plato associated with the elements of the cosmos. Plato assigned the dodecahedron to the cosmos itself, not to fire or earth or water, but to the totality, the order of all things. The choice was philosophical, not physical. Plato had no way of measuring the cosmic microwave background. But the intuition that the universe might have a specific, elegant mathematical shape predates modern cosmology by 2,500 years. If the universe is in fact a Poincaré dodecahedron, then the modern data has stumbled into a configuration that ancient philosophy guessed. This is not proof. It is not even strong evidence. But it is a striking pattern. A pattern that materialism dismisses as coincidence. A pattern that the theistic worldview interprets as the natural fit between the structures of reality and the categories of human understanding. Reality has a shape. Human reason can guess at the shape. The guessing is not random. It works. What does it mean that ancient philosophy guessed a shape that 21st century physics may yet confirm? It means that the universe is more like a designed object than a random accident. Designed objects fit categories of thought. Random accidents do not. There is one final thread to pull: the information content of the universe. If the cosmos is finite, with a specific topology, then it has a maximum information content. The Bekenstein-Hawking bound, derived from the thermodynamics of black holes, states that the entropy of a bounded region cannot exceed 1/4 of its surface area in Planck units. For a universe of horizon radius approximately 46 billion light-years, the surface area is roughly 2.4 times 10 to the 53rd square meters. The maximum entropy is on the order of 10 to the 123rd in dimensionless Boltzmann units. The current entropy of the universe, dominated by the radiation of the cosmic microwave background, is approximately 10 to the 88th. The universe is far below its information ceiling, far below its capacity, far from its maximum possible state of disorder. This is itself a fine-tuning problem. The natural state of any system, given thermodynamic considerations, is to be near maximum entropy. The fact that the universe is so far from maximum entropy means it began in a state of extraordinarily low entropy. This is the past hypothesis. It is the reason the second law of thermodynamics has anything to do at all. And it is the source of Penrose's estimate of 1 in 10 to the 10 to the 123 improbability. The universe began in a state so precisely tuned that the deviation from any randomly chosen alternative is beyond the description of human numbers. The Poincaré dodecahedral topology, if it is the true shape of space, only sharpens this fact. Because in a finite universe, the configuration of the initial state across the entire cosmos is even more constrained than in an infinite one. A finite cosmos, with the observed low entropy, requires the entire bounded region to be specified at the moment of the beginning. There is no infinity over which the precision can average out. Whatever set those initial conditions had the power to do so, had the knowledge of what was required, and had the will to actualize one specific configuration out of an unimaginably vast space of alternatives. Power, knowledge, will. These are not the attributes of unconscious matter. They are the attributes of mind. This is where the evidence leads. Not to certainty about the precise shape of the cosmos, not to confirmation of the Poincaré dodecahedral model, not to a definitive answer about whether the universe is finite or infinite. The data does not give us that. The data gives us a precisely tuned configuration of constants, geometries, topologies, and initial conditions, all of which are specified in ways that exceed the explanatory power of any naturalistic framework. The universe is the kind of thing that bears the marks of having been chosen. You can resist this conclusion. The materialist tradition has resisted it for centuries. The resistance has produced ever more elaborate frameworks, multiverses and anthropic selections and brute facts, each more speculative than the last. None of them explain the data better than the simpler hypothesis that the universe was produced by an intelligent cause with the power and the knowledge to do so. The cosmological argument was not invented to support a religious tradition. It was discovered by reason, examining the structure of reality and following the implications wherever they lead. It says that whatever begins to exist has a cause. The universe began to exist. The cause is therefore not the universe. It is not bound by space, since space is part of the universe. It is not bound by time, since time is part of the universe. It is eternal. It is uncaused. It is self-sufficient. It is the kind of thing the theistic tradition has always called the Creator. This is what the evidence supports. This is what the cosmological structure of the universe, examined honestly, indicates. The precision is real. The fine-tuning is real. The improbability of the configuration is real. The intelligibility of the universe to human reason is real. None of these can be explained by chance. None can be explained by selection from a hypothesized multiverse without itself invoking deeper fine-tuning. None can be explained by appeal to future science that does not yet exist and may never come. The rational alternative is that the universe is the kind of thing that exists because something with the power, knowledge, and will to create it chose to create it. The dodecahedron, if it is the shape of the cosmos, is one more piece of evidence that the design is precise. The matched circles, if they exist below our detection threshold, are one more piece of evidence that the architecture is mathematical. The flatness, the quadrupole, the constants, the topology, the past hypothesis all converge. The materialist worldview tells a story in which all of this is accidental. The theistic worldview tells a story in which all of this is intentional. The data does not adjudicate between the stories with certainty, but the data is consistent with intention to a degree that no honest examination can dismiss. The materialist story requires an enormous catalogue of unexplained brute facts. The theistic story explains those facts as the natural consequences of a creator who has power, knowledge, and will. Reason follows the evidence. The evidence, examined honestly, leads here. Let me bring this exploration to a close. We began with a question about the shape of space. We have ended with a question about the cause of the cosmos. The journey from one to the other was not a detour. It was the natural arc of any honest inquiry that follows the data far enough. The shape of space, on close inspection, depends on the values of constants that are themselves not explained. The values of those constants are tuned with a precision that mocks the word coincidence. The precision points to specification. Specification points to a specifier. Cosmic topology may eventually tell us whether the universe is shaped like a Poincaré dodecahedron, like a flat 3 torus, like a sphere, or like an infinite plane. The answer, when it comes, will be one more piece of an architecture that, taken as a whole, exceeds any naturalistic capacity for explanation. The matched circles, if they exist, are still beneath our detection threshold. The quadrupole anomaly, if it is a signature, is still ambiguous. The flatness of space, however measured, remains a precisely balanced configuration whose existence requires explanation. The materialist response is silence, or speculation, or evasion. None of these is an explanation. The theistic response is that the universe is the kind of thing that exists because it was caused to exist by something eternal, intelligent, and free. The cause is not part of the universe. The cause is not bound by the universe. The cause is what the universe points to. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Sleep well tonight, beneath a sky whose shape we may never fully measure, in a universe whose precision we cannot fully explain, surrounded by an architecture that, examined honestly, points beyond itself. Good night.